I felt kind of, I got it on Friday. I went hiking on Saturday. Sunday, I felt a little dehydrated and washed out because I went hiking in Phoenix, of all places. It wasn't too hot. Okay. But generally, this chart generally works if you kind of know the rules and what RL is and what RD is and where they're at. We went through this, and yes, this is kind of a big deal for me. If I give you, and I've done this before on the exam, I don't know if I'm going to do it again or not. If I give you for stage 1, I'm back to white. Stage 1, if I give you the input resistance, the output resistance, and the gain, and I give you the input resistance and the output resistance and the gain for stage 2, and for stage 3, I give you the source resistance, and I give you the load resistance, and I don't give you this diagram, can you draw that diagram and put the resistances in the right place? And can you use a voltage divider to calculate the gain? I will probably continue putting that on the exam until I'm satisfied that the world understands that, including the engineers at Microchip. So that is a useful thing to know. We went over that last class. Now we're going to look at some biasing schemes, different ways people get the DC voltages to the circuit. Biasing is setting up the big ID and the big VGS, and also it sets another important thing, the big VDS. Generally, you're shooting for a fixed current because you've got a power budget for your circuit. And so that fixed current determines what VGS is. You also need a fixed current and a fixed VGS. You can vary the size of the transistor. And we're going to look at some circuits that do this. So this one is really, the one on the left is my favorite. The way we deal with this one is the first thing I say is VS equals 0. And VG is just a voltage divider because the current going into the gate is 0. So VG will equal whatever this is, VDD times RG2 over RG1 plus RG2. Okay. We can, if we know the current, or we get a little bit more information about the drain, some more information about that, a little bit more information. If once we know the VGS, we know the current. And if I know either VD or choose VD to get best linearity, I can figure out what resistance value I want to put there. This one's trickier. The one on the right, I don't like this one so much. What happens here is you end up with, you're going to have different RG1 and RG2 because this VS does not equal 0. It equals whatever the drain current is times RS in this case because it's grounded. So that is one equation. The other equation is basically, we've got VGS. We can do the saturation equation. You end up with a system of quadratic equations unless I magically just give you ID. If I give you ID, you can solve this one. That's the only way I would ever put this. So yeah, here we go right here. Let's do it. VDD. I love you, McAfee. The virus program I can't get off my computer. We've got, what have we got here? Oh wait, did I skip one? Yes, I did. I think I went backwards. Okay, so VDD is 1.8 volts, and that's what is tied to both of these. The arrows indicate the positive power supply. I'm given the threshold voltage I'm given Kn prime and W over L. Now, it tells me what my design goals are. I want the drain current to be 100 microamps. I want minimum power. So for minimum power, I am going to, well, we'll get to that. I'm given this other guideline here too. What I want to do is I want to drop 1/3 of the voltage across RD, 1/3 of the voltage across RS, and 1/3 of the voltage across the transistor. So that means I'm starting out with a 1.8 volt difference. I'm going to have 0.6 volts here, and I'm going to have 1.2 volts here, and I'm going to have 1.8 volts up at the top. So that's going to help me out a little bit. That's going to help me out a whole bunch. Was I given anything? I wasn't given any of the resistor values. Let's go back one. 44. I just want to see so I don't get on a rambling thing here. Okay. We know ID, we can figure out what VGS is. VGS will be the square root of 2ID Kn prime W over L. Is it minus or plus? It is plus VT. Okay, that's just from the saturation current equation. I've got numbers for everything. I can plug them in and I get VGS comes out to be 0.5 of a volt. I immediately add that to my schematic because this is going to help me figure out what VG is. So this is 0.5 volts. And I've got 0.6 plus 0.5 must be this gate voltage. So I've gone 0.5 of a volt above 0.6 volts. It's a version of KVL. This is 1.1 volt. Now I know kind of what the ratio of RG1 and RG2 are. What did I do? I chose RG2. So I've got a voltage divider here. I know if I want 1.1 volts out of my voltage divider. I've got 1.8 volts in. That will equal RG2 over RG1 plus RG2. So I've got to pick one of those values. I'm going to pick a fairly large value because it's not going to affect anything other than that gate bias. And I don't have any current flowing in there. So in order to minimize the current drawn in that voltage divider part, I'm going to make RG2 big. Usually people pick this in the megohms or the tens of megohms. I just picked, I'm the designer, I can do this. RG1 equals 1 megohm.
We actually solve for RG1 based on what we got, but we just have to pick values.
It's one equation and 2 unknowns. So you've got to pick one of the values and you can solve for the other one. That happens a lot, and that was the hardest thing for me to get a hang of. Because wait, I have some control here. I picked a big value, and
Mega or milliohms?
That's mega. That's very definitely megaohms. Which one did I pick? I probably picked did I pick RG1? Why would I do that? No, I picked RG2 because it's easier to solve if I pick RG2. And I got RG1 was 606K. So that's how I get to that side. Now over here, I've got voltage drop and I've got current. So RD, I can define that one. This is just Ohm's law. The voltage drop across it, 1.8 minus 1.2. V equals IR. Why do I still have to do that? V over I. I was doing it right. Divided by 100 micro. And so RD comes out to be 6K. And I can do the same thing with RS. Now, this is a really easy way to mess up kids on the exam. Is if this isn't ground, if this was like minus 1.2 volts, then if I apply Ohm's law here, it's 0.6 minus negative 1.2. There's a 1.8 volt drop across there. Okay, I've warned you. In this case, 0.6 minus 0. So RS is going to be 0.6 over 100 micro. ID equals IS. So I can get a value for RS. And did I do the? It's going to be 6K ohms too. Yeah, it's still 0.6 of a volt drop. So it's still 6K. Yes.
Quick question. So when if you do happen to have a negative power supply on
Yes.
negative ESS or whatever it would be called, is it always going to be the same absolute value as the positive power supply, or going to be different?
It can be different. In most analog circuits, they have the same magnitude. There was this horrible family of logic back in the 70s, and they actually built memory with it, that had a positive 5 volt supply and a negative 12 volt supply.
For your RG2, why did you choose 1 mega ohm? Was it like arbitrary choice or some?
It was a semi-arbitrary choice. I wanted it to be big. Usually the resistors you use for the gate divider in this circuit are usually in the megohms. 10 megohm may have been a better choice, but I just picked a value because I want them to be big because I want to have a smaller current going through RG1 and RG2.
Okay, that makes sense.
Yeah. If I could get by with 10 megohm, I would be better off. The trade-off between, if I have a bigger resistor value there, I'm going to have less current, and that seems like it's a really good thing. Except bigger resistors actually produce their own noise, their own random fluctuations based on the current flowing through them. And the bigger the resistor, the more noise it produces. So it's a trade-off between noise and how much current I want to do.
A question.
Yes.
So on the homework, we had something similar to this.
Uh-huh.
But we weren't given a rain current.
Okay, I'd have to look at the specific problem. I don't think I did anything quite like this without a drain current.
Actually, it was a different circuit.
Okay, yeah. We can look at it. If you can give me like a specific problem, and then I can look at the circuit and kind of tell you what's going on. It's hard to tell without a picture. Okay. Now, when we build these amplifiers, there are a couple things going on here. I've got this signal voltage here that could be coming from a high impedance source. I do not want the DC VGS going back into my signal source. So the trick we use to do this, and on a lot of schematics and textbooks you actually see this, is you have capacitors with a value of infinity there. Yeah.
That's not the same case when you do small signal and have an infinite R.
No, this isn't infinite. Okay. Let's look at the impedance of the capacitor and figure out what the capacitor is doing in this circuit. It has nothing to do with I equals C dV dt, thank goodness. Or charge sharing even. The impedance of a capacitor is 1 over SC, or 1 over J omega C. Sorry, I've been teaching 280. 1 over J omega C. If I'm at DC, that means the frequency is 0. Omega equals 0. which means the impedance of the capacitor is 1 over 0. So ZC equals infinity. That's an open circuit. Now, if omega, I already got that one. Now let's say omega is really big. We go out to omega equals infinity. We'll call AC approximately omega equals really big. I'll just call it really big. Then I have 1 over a large number, Z, which means I'm going to approximate ZC approximately equals 0. This will work for my midband. We'll talk about what I mean by midband in a minute. So I have two cases here. The DC equivalent of my capacitor is it's an open. The AC equivalent is it's a short. It's basically called, that capacitor right there is called a DC blocking capacitor. It keeps the DC from the gate from getting into my signal source and corrupting it. If I want to draw the AC circuit for this, remember, okay, we've got the capacitor here. We know how to deal with the capacitor. The capacitor just becomes a short. Now we want to look at our DC sources, and this is important too. So for the AC circuit, we're going to take the DC sources and deactivate them. And voltage sources that get deactivated become shorts. Current sources are going to go to opens. It's the rules of parallel impedance. It has to do with Thevenin, and you don't want to hear me talk about it. Okay, but that's basically the rules I'm dealing with. So this DC power supply up here, this VDD, is really an AC short to ground. And this becomes an AC short to ground. That's the AC circuit right there. Is I've got my capacitor shorted out, my signal is going into RSig, and since both RG1 and RG2 are going from the gate to ground, they're in parallel. Okay, we'll draw pictures in a second.
So the voltage drop across RG1 and RG would be the same.
Yes, in that case. Well, yeah, because the AC voltage drop across both of them would be the same. The DC voltage drop is going to be different.
Yes.
Yeah.
That's for the AC circuit, right? So RG1 is RG2 for the AC circuit.
Um,
When they're equivalent.
no, for the AC, there's still fixed resistors on the board, so they'll have different values. I only get one physical resistor to put there, so I've got to keep them the same values. Okay. When do I get to that? Eventually. Now let's look at this one. This is a DC circuit, and I don't know why this is thrown in here. I tried to make this make more sense. ID is 100 microamps. So ID is 100 microamps. What is the current through the RG resistor? It's 0. Current going in the gate always has to be 0. I have 0 current going through it. I have 0 volts across it. Ohm's law still works. So in this case, VD equals VG. Why did I put that resistor there if it doesn't drop any voltage or current? It's a stabilizing thing again. When if I'm switching or if I have some AC signal coming in there, it slows down. It gives me an RC time constant between the gate and the gate capacitance and the resistor. I get some delay in there. It slows things down, so it tends to stabilize things. Those are usually like 100 mega ohm resistors.
So it's almost like a bypass.
Yeah, it's kind of like a bypass circuit. It's just it's putting an extra pole there. If you can think in terms of Bode plots, we'll get to that after exam 2. And we want minimum power. How does that? What's the point here? Okay, so we've got 100 microamps. That 100 microamps, I can plug that back into the saturation equation, VGS, square root of 2 ID over Kn, plus or minus VT. How did I do that this time? I just solved for V over voltage, plus VT. So we can get VGS is 0.76, 0.716 volts. So that means this is 0.716 because the source is grounded. And since there's no drop across this, the drain voltage is also 0.716 volts. So I can find RD at that point because I've got voltage on both sides and I've got current. RD is just from Ohm's law. RD is 1.8 minus 0.716 over 100 microamps. So in this case, we pick our RD to be 10.8 k ohms, or as close as we can get. In reality, resistors come in certain sizes, so you just kind of ballpark it and get as close as you can.
Can you explain why VD equals VG again?
Okay, so VD, I have no gate current. The only place for current to travel through RG is it has to go into the gate. And since there's no current through RG, there's no voltage across it. So the voltage on both sides of it has to be the same.
Okay, that makes sense. Thank you.
Okay. If we want to find the maximum the signal range of VD, the maximum voltage would be when the AC current actually drops the total current to 0. So VD max would be 1.8 volts. And to get VD min, I would have to, that would be, I'm using this equation. This is the equation that determines whether it's in saturation or not. VDS is greater than or equal to VGS minus VT. I could add VS to both sides, so VD min is, oh great. VD min is going to be VG minus VT. So 0.716 minus 0.4, yeah. So VD min is 0.316. And so my signal range on the output would be between 0.316 and between 1.8. If I looked on this on an oscilloscope and I put an AC signal in, I fed an AC signal in here somewhere, what I would see, and I cranked up the AC input signal, I would see that it would actually saturate when it goes out of saturation at 0.316 volts, and it would like flatline.
So what is the minimum force specification? Because it looks like you designed this for full voltage swing.
Yeah, there's no AC signal on here. I don't understand this completely. Hold on, I'm actually going to read this. I just want to see this. Okay, I can't read this. It's like 12 paragraphs long. It's a text message that's 12 paragraphs long. Okay, never mind. Go ahead.
So it looks like with the Fusion Max and Heating and
Yeah.
it looks like you designed this for full voltage swing.
I haven't really designed this for any voltage swing. I've designed this to have 100 microamps DC current flowing through it.
So where does the minimum power come into play?
The minimum, not in this one. If I wanted to do this with minimum power, what I would do is, okay. If I wanted to do this for minimum power, I would set this to 1.8 volts. I would lower this current. And it minimum, some pieces of the slide don't make total sense to me, because when you talk about minimum power, what you do is you find a bias point on the voltage transfer curve. So, and let's redraw this again. So for minimum power, I would put the Q point right here. I have no AC input in here to vary it across here. So it's just not quite.
So you can say minimum power as long as you specify how much voltage swing you need.
Right. If it was minimum power, what I would do is I'd set that current down to 0. Okay, that would do it, and I would change my value of RD. But I can't. The power's not going to change if the only current I have going into it is 100 microamps DC. I need an AC source to change that power.
What about our width and length? They have lambdas next to them.
That would change. It still doesn't change the current. The only thing that can change the current once I set the current is another AC source. What I would do if I had some AC source in here somewhere, let's just imagine one in here. So I put some AC source up here. Then the AC source would vary the operating point about this. And the current would be varying between whatever the minimum range was. But if I'm at 100 microamps, I'm probably somewhere down in here. Setting the current kind of like blows the whole minimum power thing out of the water.
What does the lambdas represent on the width and length?
Oh, on the width and length, if you look at the lambdas, if you look at the TSMC 018 text file, up at the top, there's a number that says, or a lot of times on the top of the homework, it says lambda equals 0.09 micrometers. Lambda is the minimum feature size that I can build in that process. So usually every piece of the process, every wire you draw, every end well you put in is a multiple of lambda. And then that way everything kind of lines up on a grid, and it keeps things from like overlapping accidentally by a little bit, or having little gaps somewhere because you didn't use an integral value of lambda.
We rely on lambda being that value for every problem in this process.
If I tell you to use a TSMC 018 data sheet, then you can use that one. Occasionally, sometimes on the exam, I flip processes and I give you the numbers, and I give you the numbers on the front page. So sometimes I go to the 013. The homework is mostly 018. Okay. This is a constant current source. This is amazing. Okay, I've got this amplifier here. And then there's no AC signal in it. This is just some generic amplifier we're not going to worry about. The piece of this we want to worry about is really M1 and M2, the current mirror part of this. We have a negative power supply. So we have negative 1.8, negative 1.8, positive 1.8. We got threshold voltages. We've got the W over L, that is 10. That reduces to 10. that is of M1 and M3. We don't have any information about M2. We want the drain current on ID1 to be 100 microamps. And we want the drain current on ID2 to be 500 microamps. Okay. We're not given R1 and R2. Okay. For M1, this is when you start getting multiple transistors in a circuit, you've got to be careful when you label things. So for M1, we know it's current. We can find VGS of 1 is going to equal 2ID1 over Kn prime W over L of 1. And VT is a constant, plus VT. So we can get VGS1. And this was 47. What does that come out to be? VGS1 is 0.716. So I go ahead and label that one. Okay, so I've got minus plus 0.716. So what I need is I'm going 0.716 volts above minus 1.8 is going to be about minus 1.1. I kind of estimate those to make sure I get them right before I put them in. What is that? That is minus 1.08 volts. So this voltage right here is minus 1.08 volts. That also equals the drain voltage over there, because they're strapped together. So now I can figure out R1. R1 is V over I, 1.8 Ohm's law, minus negative 1.08. If you think about this, if you're going from a positive voltage to a negative voltage, the difference is going to be greater than it's going to be like the sum of the two. So be careful. It's minus and it has a negative value. Be careful with your signs. Over 100 microamps. And R1 is 28.8 K. So I put this in, I probably put this in an IC, and I have an external reference resistor that controls the current value. Okay, I know VGS of M2 has got to equal VGS of M1 because their gates are tied together and their sources are tied together. So this is also 0.716. But we want 500 microamps out of it. So I go back to the saturation current equation. ID2 is going to equal Kn prime W over L of transistor 2 times VOV squared. Okay, my VOV is VGS minus VT is 0.316. Kn prime is given. We can calculate W over L. And we know ID2 is 500 microamps. So W over L of that second transistor, oh, stop it, Chris. W over L of the second, that's going to go off for a while, I'm sorry, is going to be 50. Now look at this. I've got 5 times the current here. My W over L is 5 times as big. It's kind of a rule of thumb. If I want more current, I just make it the transistor bigger by that size. And I can do that by just scaling the transistor values.
On the equation for ID2,
yeah,
we have Kn prime with over length for the second one, and then what is that with VD?
that says VOV squared. That's just the saturation current equation. Okay.
So the I'm sorry, the VGS reading is 1.08 volt. The VGS is 1.716. How we count that, right?
Yes. Yeah, we started out with the first transistor. We said we want to draw 100 microamps on the first transistor. And we use that to find its VGS. And the VGS is going to be the same. And I can put more I can hang more transistor. I could put an M4 and an M5 and an M6 off of here. And I could match the current or ratio the current just by varying the W over L sizes. And they use this for biasing in ICs a lot. Like that op-amp circuit I showed you, I told you, there's the gain transistors and everything else is a current source. That's pretty much what they're doing. Their current sources are their active loads. They're acting like resistors, which are kind of like current sources.
So M1 just means the wavelength of the first transistor.
Yes.
So we just multiply that by 5.
Yeah.
The same overdrive voltage.
Yeah.
And prime. So.
And you get 5 times the current. Okay, so for these nonlinear circuits, we're going to spend the rest of the time here mostly being able to draw. I'll kind of assume we can do most of the circuit analysis. The way we solve them, we find the DC operating point, find ID, VGS, and VD. That says V out. We do the small signal analysis to find ID, VGS, and VD. And we do the superposition of the two values to add them together. And that's kind of what we've been doing on when you're on part number 2 of the homework today. What we want to do now is we want to be able to draw those equivalent circuits. There has never been a 380 exam 2 that I have given that has not had a draw the equivalent circuit problem. Draw the AC circuit, draw the DC circuit. Well, that's going to be the rest of this class. If you know this and you can figure out which one's RD by looking at the equivalent DC circuit, you can do all these calculations. We're going to do a bunch of them. Yeah. The real world. Okay. If you're building an amplifier and you're building it on a printed circuit board or you're breadboarding it, MOSFETs aren't good transistors. A better transistor to use is a BJT. It has better bandwidth. It has better gain. It's got some weirdnesses to it. But we usually use NPN transistors on a board. The other thing that NPN transistors have is they're not as static sensitive as MOSFETs. So carrying them around in your pocket isn't going to damage them. But inside of an integrated circuit, it's usually the only choice we have because our process is pretty much geared towards making MOSFET transistors. You have to pay extra to get BJTs, a lot extra, like tens of thousands of dollars per wafer, inside an integrated circuit. We use, everything we've been looking at so far has had those resistors in there. So these are like MOSFET circuits on a board. Eventually, what we're going to get to when we get to the 04 slides on Tuesday is we are going to replace those resistors with transistors, replace the ideal current sources with these current sources like I've just shown. Yeah. Now, when you're building a discrete circuit, you're building something on a breadboard or a printed circuit board. The resistors are really cheap. They're like pennies or tenths of a penny a piece. The capacitors may be a penny, and the transistors may be 5 cents. So you're going to use as many resistors as you can, use capacitors when you need to, and have one transistor that the whole gain stage is based around. In an integrated circuit, your cost depends upon the area. Resistors are huge. You don't use them. Transistors are dirt cheap. So I use transistors as resistors. I use transistors as capacitors. And capacitors, you can get a couple of picofarads, but that's about it. So yeah, you're going to use all transistors when you're building an integrated circuit. And most of the stuff in Arizona is building integrated circuits. We went over this yesterday. Yeah. I can replace these resistors with transistors. I can replace these current sources with transistors, and I am got a much cheaper circuit.
So if you're replacing a resistor with a transistor, what part of the transistor would you change? You want to say more resistance?
Okay, so to get more resistance, you want more voltage drop across it. You want more VDS. So you have to kind of like look at the circuit and get it biased up so you have a bigger VDS. If you think about the triode region and the part of the curve where it's really steep, that was back in the old days, they called it the VCR region, voltage controlled resistance. And the resistance actually changes with voltage. So you can just change the drive voltage on it and change the resistance. The resistance equals roughly, it's 1 over Kn prime W over L. If I make the W over L bigger, I make the resistance smaller. Okay, and there's my multi-stage amplifier again. How much time? I got 25 minutes. Oh, I'm not doing too bad. So this is what we want to do. We want to be able to draw the DC and AC circuits. Remember, capacitors, the Z capacitors are DC open, AC short. Voltage sources, DC voltage sources. DC voltage sources are in the circuit. In the DC part of this, we leave them in. In the AC part of this, basically what we're going to do is we short them out. So generally they become shorts to ground. DC current sources, the rules are reversed. In DC, they get left in. Left in. And in AC, they become opens. And that's basically, we're just deactivating the source. We deactivate AC sources. I have never seen an AC current source in any of these circuits. The AC current voltage sources just get shorted out when I'm doing the DC circuit. And we'll go through a couple of examples. We'll go through a whole bunch of examples here. Now, if I look at this, I've got my input, my signal is right here. My output's labeled V out. So my input's on the gate, the output's on the drain. I don't have a resistor down here, so this is a common source amplifier. And to draw the DC equivalent circuit, I'm going to open up the capacitors. I'll be back. Slide 50, slide 24.